Hello everyone, welcome back. In this video, we will be looking on how to connect your Ignition Gazebo simulation to the ROS-MCP server. The ROS-MCP server allows you to control your ROS-operated robots and simulations using natural language and LLMs through the Model Context Protocol. In this video, we will be looking at how to set up a simulation environment using Gazebo, building a launch file to connect the Gazebo to the MCP server through bridges, setting up the client to start giving instructions, and towards the end, we will see a demonstration of the MCP server in action. So let's start. Gazebo is a simulation tool which allows you to quickly make robotic simulations and world environments using the .sdf files. First, let's try to install Gazebo on our computer. Please note that I will be using ROS Humble on my computer and for the purpose of this demonstration. To install Ignition Gazebo, please enter the following command. And this should install the ROS Ignition Gazebo package to your particular computer. I've already installed it, but for you it should take around 5 minutes. Now, in order for you to test your installation, go ahead on this link on the ROS2 documentation where you can launch a sample simulation using the command. So let's try to copy this. And you should be able to see something like this simulation where you can move it with your mouse. This indicates that you've successfully installed Ignition Gazebo package to your computer and we are ready to now connect it to the ROS-MCP server. Before doing that, let's try to install the ROS-MCP server to our computer. To begin with, let's go ahead and open the repository on GitHub. As you can see that this is the official repository of the ROS-MCP server. Let's try to install and use this on our systems. We can do it using two ways. We can either use pip install or we can directly clone it from the source. So for the purpose of this demonstration, we'll actually be doing it from source. So for this, let's try to go to the documentations in the docs part and open installation from source, and let's open installation.md. So for the installation from source, we'll try to clone the repository. So let's try to copy this command and go back to our terminal. I'll expand this. And I would like to clone it on my desktop, so I'll change my location to desktop. And then I'll create a repository for ROS-MCP related folders. And I'll go to my ROS-MCP folder and I'll clone it here. And this is now done. I'll just do a quick ls and it's here. I'll clear the terminal. So now we have the ROS-MCP server with us. Now in order for us to interact with the ROS-MCP server, we would need a ROS-MCP client. Now you can absolutely use a desktop application like Claude or Cursor to sort of configure your MCP server like a ROS-MCP along with the LLM provided there. However, if you would require no installation of such apps, we've also built a MCP client which already has the configurations done for you. So you can also use that. And for the purpose of this demonstration, we'll be doing that. So for you to install the ROS-MCP client, you will see this repository robot-MCP client. And then we'll actually be cloning for develop branch of this particular repository because it has the latest features and has integrations to the latest LLMs. So we'll go ahead and copy the URL of this repository and come back to our terminal and we'll clone the specific branch. So we want to clone the develop branch and then I just want the single branch to be cloned. And then I'll paste the URL of the repository. Alright. So as you can see that now we have both the MCP client and the MCP server with us. Going ahead, we'll actually be trying, now let's try to configure the MCP client to have the API keys for the LLMs as well as put in the location of the server.py files. So if you go on the ROS-MCP server, you'll actually see that there is a server.py file. This is kind of the main file which is handling and has all the toolkits for our MCP toolkit. And basically the client needs to have access to this particular file or the location of this particular file when it starts. So we'll we'll try to start a new terminal, and in this terminal, we'll try to go to the ROS-MCP client. So let's go back and go to the robot MCP client, and I'm now in my MCP client server, and I'll do as you can see, there's a shell script setup.sh. Now this will do all the essential setups, including creating a .env file, which can then be used for us to store the environment variables, which includes the API keys for the different LLMs that we may use, the configurations, as well as the location of the server file. So now let's go ahead and change the permissions of this to executable of this file, and now it's done. I'll just try to quickly run this. Okay, it's also created a virtual environment for me. However, I wouldn't be activating this. I'll do a quick UV sync to make sure that I have all the dependencies with me for this client to run, and then I clear my terminal. After doing this, I would then do a quick ls and ls-la to see that I have this .env file, and if I were to look at the contents of this, okay, .env, as you can see that there's multiple API supports, including OpenAI, Anthropic, and Google, and there's a variety of open source availability of models as well, which includes Llama, GPT-OSS, and the provider for us is Grok. So Grok, it doesn't really require a payment from you, and you can get a free API key from them. However, you may also wish to use any OpenAI, Anthropic keys, or Gemini keys, so to say. And then if you see this LLM provider, that basically allows you to choose the LLM provider from the given choice, or from these given options, and you can obviously change it. So right now by default it's GPT-OSS, and then this is the examples, the server path that I just mentioned. So I would prefer to use VS Code to edit this environment file, so I'll just open VS Code on this folder, and let's go to our environment file, and let's change the server path. Let's add a server path. So for the server path, I'll just go to my server, and I'll just find the server path. This should be a server path, and I'll copy it from here and paste it as the path here, and this should be done. Now let's try to get a Grok API key. So in order for you to get that, you just have to go to the Grok's website, and let's do a quick Google search. This should be the API key, and we go and start building. It should get to your login page. I've already logged in, so I should get to my dashboard. And then we go to the API key section, and then we can create an API key from here, and let's just name it ROS-MCP. So I've already created a bunch of them, so I'll just name it ROS-MCP5, verify, and then submit. It should help us create a API key. Okay, so now this is done. Make sure that you copy it, and we'll just paste it in Grok API key. Alright, so now with this, you successfully set up your MCP client, and we are ready to sort of use the server itself. One quick thing before we actually start using the server is the fact that we would require a ROS-bridge to communicate between the server and the ROS operating system between the robots. This helps in transferring the messages from whatever the LLM or the MCP is providing to the ROS and vice versa. To make sure that you have the given requirements, go on the installation.md file in the documentation, and then if you go down, you'll actually see this on the target robot on the installation of the ROS-bridge server. So make sure that you copy the commands. If you do not exactly know your ROS distro, I would recommend using the environment variable, and it would by default do your own ROS distribution. So let's try to copy this and go on a terminal. We'll paste it on a terminal. It asks for a password. We'll give it. And as you can see that I already have the server, so I don't have to it didn't install it, but for you it will install it.
With this, you've now completed the installation of both the server and the client. Next, head over to this link, which includes the demos of the ROS-MCP server. I will now copy the link of the repository and quickly clone this on my local computer. Okay, now this has been cloned. I'll go to the following folder and open VS Code from there. As you can see that this is the project structure. It contains or the .sdf files, the launch file, as well as the following readme and the pyproject.toml for the UV environment. For this example, we will be using a sample tugboat simulation environment which was downloaded from Gazebo Fuel, and here is a link for it. Now let's look at a brief introduction of the SDF files. You may want to use your particular SDF files or your simulation files, and you can incorporate this in place of this particular file. However, each SDF file will contain these three different parts. Number one, it will contain the world. Now, the world is the environment and the robot description in which your simulation will be there. The second thing will be the physics engine. As you can see that this is the physics tag of the simulation, where we define all the different physics as to how the environment will interact. And the third thing will be the plugins. And these plugins can also be downloaded as well as created by you as well. Moving on, let's take a look at the launch file for a tugboat robot and the changes required for you to adopt it for your own robot and simulation. The launch file is essentially an all-in-one script and it handles the three distinct jobs for us in the simulation. The number one, it runs the simulation, the physical engine, which is the Gazebo. Number two, it translates Gazebo signals, which are in Ignition Gazebo transport format, to ROS2 signals, which is in the DDS format. And number three, it provides external access, which means that it opens a WebSocket door, ros-bridge, so that the AI and the MCP client can enter. Now let's take a look at the first part of our launch files. The first section defines the world file, loading up our Ignition Gazebo file. If you're using your own simulation, make sure you replace this with the exact path of your own simulation. This part essentially runs the world file using the Ignition Gazebo command. Moving on, as we saw that Gazebo and ROS communicates in two different languages and we require a bridge to translate these two languages. And that's why we use ros-GZ bridge for the same. Now we'll make a note for this particular one. The arguments that you see here are essentially tells the bridge which topics to move forward. The syntax for these topics are as follows, which is the Gazebo topic name, which is this, followed by an @ the ROS message type, and the ignition message type. Then we move on to the remappings, where the particular ROS topic names are renamed into something else, which are much more easy for the MCP and the AI to read and instruct to. Now, in order for you to find your own specific arguments, you'll have to first look at and verify what are the different arguments. And for this, you can try ignition topic L, and that should give you essentially the list of all the topics that are available. As you can see that I have my world simulation file running right now, and I have these following topics available, which is for LiDAR, stats, as well as other points that are there. Now I can use them, which one of them are relevant in my bridge, and then the MCP should be able to start recognizing these particular arguments and topics. Moving on, in the last part, we actually start the second bridge, which is the ros-bridge server. This bridge essentially bridges the gap from ROS2 to Ignition Gazebo by starting a WebSocket at port 1990. Following, we make a node to start the ros-bridge server and the ros-bridge WebSocket. And finally, we return all the nodes and the arguments in sequence. Finally, let's take a look at the live demonstration of the workings of the ROS-MCP server on the Gazebo simulation. And for this, we'll be using the first example, which is the Gazebo tugboat example. Now, as you can see that I am in the exact folder where the simulation files are present. If I do a ls here, as you can see that this has the simulation launch files as well as the .sdf files which are required for my simulation. The very first thing that I will do is I will start the virtual environment and create the virtual environment. As you can see that I already have the PyProject.toml file, which provides all the requirements for this particular virtual environment. So I'll create the virtual environment using UV. So I'll just do UV VNV, and that should create a new virtual environment. I already had a new virtual environment, but I'll create it once again. So I'll just type yes, and then I just need to activate this with source.venv/bin/activate. As you can see that the virtual environment has now been activated. I'll clear the terminal. I will try to run the launch files using ROS2 launch parameters. So I'll do ROS2 launch. And this should start up my my tugboat simulation. You might want to allow it for a second for it to load up properly. And as you can see that the tugboat simulation has been loaded successfully. And we'll start with the client as well. And our client has been initialized and connected. Now let's start giving commands to our particular simulation using the ROS-MCP client. As you see that I'm giving it command to move forward for 2 seconds and then stop. And the robot started moving. The next command that I'll ask you to do is to make a revolution and to go in a circle for exactly 2 times. So in this case, the robot should need to calculate the velocities as well as other parameters for it to do it. And it is able to do it properly. I can also ask it what are the available topics for me to publish as well as read. That was it. Thank you so much for watching the video.